Welcome to today's Explainer. Now, if you're looking for a sensationalized disaster movie delivery of climate data, well, you're in the wrong place. But if you want a calm, structured, and really methodical look at the numbers, you are exactly where you need to be. Today, we're going to break down a specific location's climate history and its conditional future. We'll be using reanalysis data and multi-model projections to build a clear, evidence-based picture together, step by step. Okay, let's dive into this. Here is our roadmap for today. First, the climate place market. 2, reanalysis back to climate history. 3, defining gridded data limits. 4, a conditional CMIP6 outlook. 5, preserving the model spread. And finally, 6, questions for local planning. Starting right off with Section 1, the climate place market. So you might be wondering, why exactly are we focusing on Chicago, Illinois today, specifically the coordinates 41.8800 north and 87.6300 west in our spotlight for July 22nd, 2026? Honestly, you might assume it's because there's some massive unprecedented weather event happening there. Or maybe that this location was just cherry-picked to prove a specific point about extreme anomalies. But the actual reason? It's much more fascinating because of its neutrality. You see, the climate place market cleared Chicago with a winning coverage bid of just 90 cents. What does that mean? Well, it's a market mechanism that selects attention. It sets up a completely transparent baseline. The market result simply directs our focus. It isn't in itself climate evidence. It literally just means this happens to be the exact patch of the globe we're critically examining today. Moving right along to Section 2, reanalysis-backed climate history. Now that we've got our location locked in, let's look at the historical data spanning from 1981 all the way to 2025, provided by the NASA Power Merit 2 service. And wow, consider that number, 2.06 degrees Celsius. Keep in mind, this is not a projection for the future, this is a historical calculation. It represents the mean near-surface temperature difference between the very first 10 complete years of our dataset and the most recent 10 complete years. It's a bold, impactful number, and it tells a highly specific story about our recent past. To make that shift feel completely tangible, let's just juxtapose the exact figures. The early decade mean in this dataset was 8.39 degrees Celsius, but the recent decade mean? That jumped to 10.45 degrees Celsius. If we draw a simple least squares line right through the 45 annual values in this period, we actually see a trend of 0.57 degrees Celsius per decade. That's a grounded directional account of historical change for this specific coordinate. But, and this is a big but, before we take those numbers as the absolute gospel of lived experience, we really need to understand the boundaries of our tools. Which brings us perfectly to Section 3, defining gridded data limits. So the crucial point here is that we're using what are called gridded reanalysis values. This simply means the data describes an abstract model grid cell that happens to contain our Chicago coordinates. It does not represent a physical local station record. We aren't looking at readings from a single thermometer tied to a lamppost in the middle of the city. And because it's an abstract grid, it naturally misses things. Imagine the vast temperature difference between standing on dense, heat-absorbing concrete in downtown Chicago versus standing in a breezy microclimate right next to the waters of Lake Michigan, where you might honestly need a jacket in the middle of July. Grid cells can easily smooth over these stark local realities like the urban form, the proximity to water, and the sparse observing networks. The model gives us a grid-scale truth, absolutely, but your actual lived condition might vary drastically block by block. Keeping those limitations firmly in mind, let's shift gears from historical analysis into a conditional outlook. Section 4, a conditional CMIP6 outlook. Looking ahead to the decade of 2040 to 2049, utilizing CMIP6 models processed by Open-Meteo, I want you to listen to this absolutely crucial quote. The available ensemble behaves approximately like a high-emissions pathway and is not a probability-weighted forecast. Transparency is everything here, folks. We are analyzing a specific high-emissions condition. We are not saying this is a guaranteed, inescapable prophecy of the future. What we are saying is, if this high-emissions pathway holds, then this is how the models respond. Complex data should never be collapsed into a single, falsely certain average just to make it easier to digest. All right, Section 5, preserving the model spread. We are focusing on 3 specific models from the ensemble, the CMCC, the EC Earth 3P, and the MPI. We're comparing their 2040 to 2049 output directly against their own 2011 to 2020 baseline. Just think about the range in their final projections. The local mean temperature change ranges from 1.68 degrees Celsius on the low end all the way up to 2.30 degrees Celsius on the high end. And this brilliantly illustrates the concept of model spread. You can immediately grasp the variance here. The median sits at a 1.80 degrees, but no single model is privileged as the absolute winner or the definitive prediction. Instead, they represent different structural ways of processing the exact same high emissions condition. This spread is a vital piece of information. It's definitely not an error that we need to hide. Now, what's really interesting is what we absolutely cannot conclude from the data we've just discussed. The historical data doesn't prove why any single weather event happened. The models can't give us certainty on local precipitation, which is incredibly difficult to predict at storm scales, by the way. And they don't perfectly capture city-scale heat amplification driven by local land cover. But you know what? These limitations are actually the heroes of our narrative. They prove that uncertainty isn't a flaw in the data. It's proof that local context deeply, deeply matters. We've looked at global models and gridded histories, sure. But how does all this apply to the ground beneath our feet?
Let's find out in Section 6, Questions for Local Planning.
I really want to leave you with this one question. How are your local institutions planning for these changes using higher resolution local records? Global grids and high emissions pathways are a fantastic starting point, but the power ultimately shifts back to the community. You now understand the gridded baseline and the multi-model spread for Chicago. So the next step is empowering yourself to ask your local planners how they're filling in those gaps, the water, the concrete, the specific microclimates, to prepare for the future. Thank you so much for joining me for this explainer. And remember, keep asking the right questions.